Okay, there's some wake up music for you. Get you all fired up for the new 2.2 notes. As you can see, we have here on the screen three different interesting pictures. We have three-dimensional first answer infinite solutions, which looks like a line, as we can see here, going on right here, a single line. And then the one that we're going to see a lot of in 2.2 is one solution. As you can see, we have a dot right there in the center. Okay, when you got three planes hitting in a single point, that's one solution. And you can see over here on the right, we have three parallel planes, so we get no solution for that. So this is a nice little start to talk about what happens when you are solving systems with three variables. So as you can see there, three different solutions, a single point, which is the one that we're going to be focusing on. But you do need to know that you could get a single line, which would be infinitely many points or infinitely many solutions, and you could get no solution. But the problem we're going to look at here should end up with a single point. And there's a couple different ways you could solve three variable systems. We're going to focus in on, I think, the easiest of those, and that's the elimination method. You could also use substitution, but boy, when you are solving for a single x or y, or in this case z, since now we have three variable system, it could get very, very cumbersome using the substitution method. Elimination is still a lot of work as well, but substitution, I think, is even worse. So let's go ahead and apply what we know. We have our elimination method that we used on a two-variable system. We can apply the same thought process with the three-variable system. So when we're looking to eliminate, we want to try to make all the coefficients in front of either x or y or z the same. So, I'm looking here and I see, in front of x, we have an understood 1, a 2, and a 4. I think that's going to be pretty easy to work with and try to eliminate the x's. So we're going to go ahead and make these first two equations have the same number. So we're going to multiply the first one by 2, and we're going to multiply the second one by a -1. The reason why I want to multiply by a -1 is because we want to have different signs. It's much easier to eliminate when you have different signs. So when we multiply, we end up with 2x minus 4y plus 2z equals 30, and we end up with negative 2x minus 6y, not minus 6y, sorry about that, minus 3y plus 3z equals -1. So we're going to add those together. As you can see, the x's are eliminated. That leaves us with negative 7y plus 5z equals 29. Okay, so we eliminated one of the three variables. So now we're going to do the same thing again, but we're going to do it with the second two equations, and we're going to now try to eliminate x with those. So I'm going to go ahead and multiply again. So the first equation, I'm going to multiply by 2, because that will give me the 4 that you can see here in the third equation. And I'm going to go ahead and just multiply by -1 in the last equation here. And that should give me the same numbers in front of x, but opposite signs, so we can eliminate. So 2 times 2 is 4x. 2 times 3 is plus 6y. And again, 2 times 3 is negative 6z equals 2. And we multiply by negative 1 here. We get negative 4x minus 10y plus 5z equals 3. Adding those up, again, the x's are gone. We get negative 4y minus z equals 5. All right, so as you can see here, both of these equations that we just created, okay, both of them, so we got negative 7y plus 5z equals 29, and we have negative 4y minus z equals 5. So as you can see in both equations, they both have x eliminated out. So now we basically turn the problem into a 2-variable system. Now we'll just go through the same motions that we did with the last section, 2.1, where we're just going to eliminate either y or z. Okay, so let's go ahead and multiply again. So we'll multiply by, let's get rid of z this time. So we're going to multiply by 1, and we're going to multiply by 5. Boy, that came out a little rough. Let's try that again. So multiply by 1, multiply by 5. Okay, so the first equation ends up being negative 7y plus 5z equals 29. Nothing really changed there. And here we get negative 20y minus 5z equals 25. So we're going to go ahead and add those up, and as you can see, the plus 5z and the minus 5z go away. So that leaves us with negative 27y equals 29 plus 25, which is 54. Okay, so getting y by itself, we divide both sides by negative 27. So if we take 54 divided by negative 27, we end up getting negative 2. So we found one part of our solution. Okay, our solution now is going to be x, y, z. Remember, our solution when we solve 2 variables was simply the point x, y. Now, since we have 3-variable system, we'll actually get a 3-dimensional point, a point in space, okay, represented by x, y, and z. So once we have y, we're going to plug it back into one of the previous 2-variable equations and get solve for z. So as you can see, if we scroll up here, we have two variable problems over here. Let's go ahead and take this over here. So I can use either of these two. Okay, they're both 2-variable equations. I'm going to use looks like the second one has smaller numbers. So I'm going to take the negative 4y minus z equals 5, and I am going to plug y into that. So I'm going to get negative 4 times negative 2 minus z equals 5. So I get 8 minus z equals 5. Negative z equals, I subtract 8 over, I get negative 3. So z equals 3. So there's the second part to my solution. Okay, so we have z is 3. Okay, we have that y is negative 2. So all that's left is whatever x is. So how do you find x? Well, we have z, we have y. What we're going to do now is we're going to go back up, all the way back to the beginning. Let's go ahead back up to the beginning. and we're going to take one of the original 3 equations. Okay, one of the original 3. I'm leaning towards this one right here. This looks like it's got pretty small numbers in it. I just have a single x, a minus 2y, a z. I do a 15 on the right, but I'm going to go ahead and take that down, okay, and use that to find the third. So we got x, okay, so again, x minus 2y plus z equals 15. So we're going to take the 2 variables that we currently have. X we don't know. We do know y. That's negative 2. We do know z. That's 3. And now we have an equation where we can solve for x. So x plus, again, it's a 2. Kind of looks like a z, but it's a 2. 2 times 2 is 4 plus 3 equals 15. So x plus 7 equals 15. X equals 15 plus 7, which is 20. Sorry, I said 15 plus 7. 15 minus 7, which is 8. So there's our third part to our answer. X is 8. So our point, our solution, okay, the single point out in the middle of space is 8, negative 2, and 3. So what does that mean? Well, what that means is that if you plug these points back into any of the original ones, for instance, here's one right here. Okay, here's one of the original 3 variable equations. If I plug these in, so if I put 8 in for x, and I put 2 times negative 2 in, plus 3, I should get 15. So let's see if this checks out. So we get 8 plus 4 plus 3, and 8 and 7, 8 plus 7 is 15. So 15 equals 15. It checks out, right? So this works. That's the solution that makes that a true statement. And if we went back up, plugged into the other 2 equations, you would see that all 3 would turn out to be a true statement, proving that all 3 would work. So our answer, as you can see here, is 8. Pretty rough 8. Let me fix that up a little bit. 8, negative 2, and 3. So that's what that's what you should be doing to solve 3 variable systems. Use the elimination method. I think that's the easier way to go. So that's it for lesson 2.2. Good luck, and get to work on that homework.